I think we can all agree that cars are probably one of the coolest inventions to have ever been created. They can literally take you anywhere you want to go in the span of a couple hours to a couple days, minus like Antarctica or something. But honestly, despite them being really amazing inventions, there's still one problem that remains with them, and that is this. And it's not trivial either. Upwards of 1.9 million people lose their lives every single year just due to car crashes, which, in this day and age, given our amazing collision avoidance systems, really shouldn't be that much of a problem. So rather than investing so much money into things like sensors, more parts, insurance claims, etc., why don't we just invest in autonomous vehicles that don't need sensors? Basically, what I'm talking about is simply mounting 3 cameras on top of a vehicle in order to make it fully fledged and able to drive itself. In other words, we're going to be using AI to simulate a self-driving car using a little something called behavioral cloning. Alright, now the first thing that we need to do is actually find a car to test this on, and I really don't want to be running an actual car and repeatedly crashing and testing it for this, so we're going to try looking at a simulator instead. And in this case, Udacity actually has a pretty sick open source simulator that's made for this purpose. Here's what we need to get an AI to work. Now, first, we're going to need training and testing data, and the way that this is going to work is that I'll be driving the car around 5 laps in either direction on their simulator. The car is based off of NVIDIA's self-driving car, and as we drive it around, it'll be collecting images from the right, left, and the center of the car via 3 virtual cameras. And along with that, it's also going to be collecting other extremely helpful data, such as things like the steering angle, throttle, brake, and the overall speed. Alright then, let's get to it. Okay, I'm gonna be 110% honest, that took way longer than it should have. Alright, next step, look at the data and see what's up. So the simulator saved the image directories and the numerical data all into one CSV file. Cool, we can access it pretty easily. Now, we need to take this data and make batches to serve them up to our non-existent model. And that's exactly what we're going to be doing next. Now, before we get started, just want to mention a quick thank you to Siraj Raval on YouTube, who provided this tutorial in the first place and whom this code is inspired of. Now, let's get into the code. Now, the first thing that we're going to be doing is that after installing all of these various machine learning libraries, is that we're going to be setting some basic values, namely batch size, test size, height, and width. Now, natively, the height of the images that the car sends is actually 160, but we just set that to 75 since we're going to be doing some cropping later on. Now, before we do anything, what we need to do is actually load in the data, and here we're using scikit-learn to split it into training and validation data. And next, here comes like a kind of a hard part, is actually defining the functions and the various things that we need to do to actually get this model to work in the first place. Now, since we aren't using a native Keras dataset and we actually collected it, we're going to have to write our own image processing and batch generation function. We're going to have to make sure that all of the images are actually the same size by cropping them, and also crop out the sky and the actual surroundings of the car and the car itself. Because the only thing the car needs to see is the road. It has nothing to do with the car. And we don't want our neural network somehow finding trends within the direction the car is facing, or maybe random trees on the side of the road. You get the memo. Alright, so we have a small problem. And the problem is that our dataset only has around 15,000 images, and I know that might seem like a lot, but the thing is that would be more than enough for an easy task, like let's say classifying apples and oranges. But with something as complex as trying to find a steering angle from roads, we kind of should probably have more data just to make sure that the network has enough data points to actually model itself on. So, we still have one other trick up our sleeve, and that is image augmentation. Basically, we're going to be taking the input images and resizing them, cropping them, rotating them to artificially create more data. Problem solved. Alright, so we've written a couple of different functions here. The first one is that of readImage, and this is responsible for taking our images from the CSV file and extracting them to be used later on and loaded into our dataset. Then, after that, we have the crop function. Next, we have the RGB to YUV function. And as you probably know, neural networks are really sensitive to minor details, and even as something obscure as the image being black and white or colored can really mess up the entire prediction modeling of the network itself. So, we'll be trying out turning it into the YUV color scheme, which is what NVIDIA did with their machine learning model using OpenCV's CVT color function. Now, there's a slight hiccup here. We have 3 different images for each steering angle, but from the perspective of each image, the angle actually looks different. Since the only thing that we're giving the model is a single image per steering angle, it's gonna get confused really quickly if it gets 3 different images, all having the same steering angle, yet the curves of all of them are completely different. It's really gonna mess up our model. So, what we have here is a choose function. And what this is basically gonna do is that it'll adjust the steering angle depending on what type of images we send to the model. If we choose to send the left image, then we'll add 0.2 to the steering angle since the road here looks more curved. And if we choose the right image, we're going to be subtracting 0.2 since the angle from this area is going to be looking straighter. And for the center, we don't do anything because the center is exactly where the steering angle was actually derived from. The next couple of functions here are pretty self-explanatory. Here, we're translating the image randomly in order to artificially create more data, and we're also going to be flipping the image, adding random shadows, and also changing the brightness periodically, so that the neural network understands that it's not really the makeup of the image that we're trying to test, but the actual curvature of the road. And last but not least, we combine this all into one gigantic augment function, where we simply just put everything together. And yeah, that's pretty much it for data augmentation. Now that we've done all the data pre-processing that we need to, we can now actually get into building the actual model. And since this is a basic case of image regression, we're going to be using a convolutional neural network, or a CNN, to get the job done here. Let's get to it. Alright, now that this bad boy has been trained, we actually need to get it to talk to the simulator and, drive the car. So what we're going to be doing is that we're going to use a server-client model for this to work, in which case our code is going to act as a server, and then the client is going to be the car. So the way this will work is that on every iteration, the client will send 3 images back to the server, and the server, on the other hand, is going to take those images, augment and pre-process them, then run our convolutional neural network on top of that, and then send the outputted steering angle back to the car, where it's actually going to drive. So hopefully this works, and let's check it out. Okay, so something clearly isn't working here. So when a neural network goes wrong, it can be for a lot of potentially mysterious reasons. The most obvious one is probably just that our architecture is messed up or something like that, but other issues can also involve things like data processing, the activation functions, or even just a typo and overwritten variable. In this case, we need to tune some hyperparameters and switch some activation functions around to get the loss pretty low. Now, let's try that again. And as you can see, it absolutely fails. So honestly, I think that serves as a pretty good testament to see just how far AI can take different technologies, especially with something like behavioral cloning. Some next steps would involve more training, more testing, collecting more data always helps, and just, fine-tuning parameters is definitely another thing that we should look into. Now, yeah, that's pretty much it for behavioral cloning with autonomous vehicles. If you're new to the channel, my name's Aditya Dwan, and I'm a 14-year-old who's currently extremely obsessed with AI, filmmaking, and productivity. This channel is a combination of self-improvement videos and more tech-based tutorial videos like these ones. So yeah, if you like this, definitely make sure to appease the AI overlords behind YouTube and, smash that like button or subscribe or whatever, honestly. And yeah, if you guys want to find out more about what I'm doing, my website and my newsletter are all linked in the description below, so feel free to check that out. And yeah, thanks for watching. See ya.